Good afternoon to everyone. So, what I'm going to present is a case of study of an urban tunnel in which geological risk got materialized and actually was quite a bit of disaster. And we did some rehabilitation to come things to normal and to put this tunnel under operation. So the presentation is about, first there was an introduction, problem statement, methodology, verification and performance monitoring, and then conclusions and takes away. Some introduction of myself, ALVARO CASASUS. I'm Chief Technical Principal in Sumana Jurong. I have over 27 years of experience in tunneling in Europe, Middle East, Asia, Australia. Currently, I'm leading the underground design for Etihad HSR. I have expertise in TBM and ATM tunnel segmental lining, underground structures. And I have been author of several papers and international conference. So the problem statement, as I said, the context. This is an urban tunnel, typical urban metro, that while boring in the ground, hit some pressurized aquifer that in principle was not expected, at least not the reaction of the ground that it has. So the complexity was that this unpredicted behavior of the aquifer produced heavy seepage through the TBM. The water started in uncontrollable manner to enter through the tail skin of the TBM. And the result of this was that the full tunnel got flooded of water, and not only water, also the ground, small particles was dragged, was coming along with the ground and was penetrating our tunnel. And the surface, we have quite severe settlements, up to 1 meter, and more than 18 buildings got severely damaged with cracks, and people who had to evacuate from the buildings, and a lot of restoration happened after that. So, geological context. The TBM, the ground in general is a soft clay mixed with soft and stiff clay. It's an alluvial deposits and intercalated in between this soft and stiff clay. There are some lenses of silty sand material, a material quite difficult material with no cohesion, and the TBM was a conventional EPB, metro EPB of 6.3 meter diameter, and the tunnel was a typical also metro tunnel bore tunnel, 5+1 ring configuration, and two 75 millimeters thick reinforced concrete segments. So, as I said, the ground in general is quite soft clay with 25 megapascal in modulus of the worst scenario. So we can see there in the picture, or in the image, how how these lenses, this yellow is the silty sandy material with no cohesion, and that strata was the one creating this big issue in our tunnel. So we just review what is, we all know what's a TBM, a EPB machine. So the EPB machine is a very safety method to excavate in tunnels, urban tunnels. It's a machine that applies some pressure on the cutter head, no? And this pressure is applied by controlling the speed that we remove the mag inside of the cutter head and controlling the advance rate of the TBM. And as long as the TBM is suitable for the type of ground, in this case it was a clay, and we add the proper additives to the cutting chamber, the water should not come to the cutter head or to the conveyor. Sorry, it's the screw conveyor. So another good point or another challenge of these TBMs is the articulation. The articulation is in the middle body. So this articulation also is a potential water path that has a heavy-duty seal there to avoid this water to come, and also has an emergency seal. It's a seal that we can inflate in case emergency, in case the water is coming for any reason, we can inflate and stop the water. So the last point, that critical point of the TBM, is the tail skin. We can see that the tail skin is the backside of the TBM. Is where we are building the segments. So in this point of the TBM, there are installed some rows of brushes, wire brushes, and also we are injecting there thick grease. And with this mechanism, we are stopping the water. We are making the TBM watertight. So what happened in this case is that this system was not enough, and the water in the ground start penetrating through that tail skin in an uncontrolled manner, and that's why this disaster happened. There is some tips here for the TBMs. No, this tail skin is quite critical. So always we need to inspect these brushes and to make sure during maintenance operation that they are in good condition, replace in case these brushes are not in a good condition. And also we need to monitor the amount of seal that we are increasing, the consumption of this seal grease, to make sure that we are applying the amount to be safe in our mining. So we defined the challenge. What happened after that? So as I said, that the tunnel got flooded with water and slush. The rains got severely distorted. You can see that the ovalization of up to 190 millimeters ovalization of the segments. Also, were some cracking on the segments. We saw cracks coming from 0.1, 0.2 up to 2.5 millimeters. Actually, it was quite systematic pattern of cracking. I can see that the coupling of the rings was clearly evident, that whenever the key was at 12 position, that cracks was not happening, and in the other segments that the bending moment was transferred, the cracking was happening. Just to have an idea, the recommendations of BTS or the recommendations for ITA, so ITA say 2.5% ovalization is acceptable amount of ovalization. In case of BTS, it's a 1% ovalization is acceptable. In our case, it's 60 millimeters, but we can see we were exceeding clearly the amount of accepted ovalization. So now, why this happened? Why this problem happened? So the mess in the segmental lining. No? We know that the water came inside of the tunnel, and there was a mess in our segmental lining. So the explanation is that the silty, sandy material, whenever it comes with a high water pressure, not having cohesion, behaves like a fluid in the end. It's not anymore a material with shear strength. And this situation creates that my segmental lining becomes without confinement. The segmental lining ring is not an structure unless it is in the ground, because it's something we have six joints, 6 hinges, so needs the confinement on the ground to be stable. So in the moment that we lose this confinement, the distortion and the formation of our tunnel happens. So what was the solution proposed? In principle, we have four approaches. So first of all, because of these distortions and this dislocation of joints, there were leakages from some of the radial and circumferential joints. So the first thing was to inject this joint with acrylic grout to make the tunnel watertight again, to avoid the leakage to happen. Second thing was sealing the cracks and injecting the cracks. So just for the durability of the structure, what we did is just all the cracks, small cracks of 0.2, 0.3, 0.5 millimeters were sealed, and the bigger cracks were injected with epoxy grout. Second thing is to reinstate the confinement of the tunnel. No, this is one of the most important interventions. So what we did is a peripheral grouting of all the affected rings. This peripheral grouting was all around the ring, and the purpose was to reinstate this confinement to put some pressurization on the ground. The ground is quite difficult. It's not a permeable ground. Grouting always is a difficult affair, actually. But the purpose of the grouting was to reinstate this confinement, to keep some pressurization around the tunnel. And finally, we designed one steel plate inside of the most affected segment. We designed this 25 plus 5, 25 millimeter steel plate. 5 was extra for durability. So this steel plate was for enhancing the capacity, structural capacity of the ring. So what is the challenge? When this came to our design office, the challenge is that we have a structure that, in principle, it seems like it's not fit for the purpose, and we need to do something. First option is to change the structure, to put another structure inside. But we can see there a cross-section of the metro project. The tunnel engineers, we try to optimize the space inside of the tunnel, and the space proofing, we make it 2 millimeter, making sure that everything fits inside, the kinematic envelope, communication, signaling, emergency walkway, everything has to fit inside. So there's not much space, actually, for putting things inside. So the first option to put one structure inside in a lining was not possible because of lack of space. And anything that need to take many moments needs to have inertia. So that's why came the idea of the steel plate, that this steel plate itself is not enough, but if the steel plate is combined along with the segmental lining, with the ring, becomes both things working together becomes a solid structure. The way of linking these two structures, steel and concrete, was with a high-strength grout, so it was a fully bonded solution between these two elements. So the first thing we did is to model the solution in finite elements. We modeled the concrete lining as a solid element, the grout, and we modeled the steel plate as a beam element. And with this 2D modeling in finite elements, we check the performance of the structure. So the results of the performance was as expected. In the positive eddy moments, means at 12 o'clock, the concrete is working in compression mainly, and my steel plate is resisting all the tensions, creating a huge enhancement of bending capacity. And in the spring level of the tunnel, the way around, my concrete is working in tension, and my steel plate is working in compression, giving extra axial capacity to the structure. So now we analyze what is the maximum capacity of this combined structure. We see that in the case, again, of positive bending moments, all the tensile forces are resisted by the steel plate, and we can use the full section of concrete for compressional forces. Means that my limitation of the structure now is not the tension anymore, because my tension capacity of the plate is huge, and I have a limitation in the compressional strength on the concrete, means crushing the concrete. In the other way around, in the spring level, my steel plate is working in compression, and my limitation is coming from the river of the segment, initial river. So the failure of the section happens because excessive tension on the river. Anyway, in both cases, we can see that the enhancement of the capacity of the structure is quite significant. So this structure, to work as it is designed as a composite structure, we need to make sure that the shear transfer between these two elements are properly resisted. So for that, we did an analysis of the shear between the interface between concrete and steel. And we calculated the shear strength about 2 megapascal, not very demanding. We found in the market one epoxy, well, not epoxy, but one high-strength mortar, able to give up to 8 megapascal of bonding strength and UCS of 60 megapascal, which was more than enough for the requirements. So now comes the point where to apply this solution. Of course, the steel plate is a costly solution, so our client, the contractor, requested to optimize and see where exactly we need, where we don't need this solution. So for the steel plate, we did this analysis of ovalization, and the main issue is that when the tunnel ovalizes, we reduce the area of transmitting axial forces. So reducing this area, this bearing area, creates an issue for being able to resist the axial forces. So in the end, what we did is checking what is the maximum mobilization that we can have, considering what are the in situ stresses axial forces in the lining. And we came to a figure of 100 millimeters. So anything coming less than 100 millimeters, what we did is just did the confinement grouting, fixing the cracks, and fixing also the gasket leakage. Everything coming above 100 millimeters, on top of that, we put this steel plate. So verification of this solution. So we did many verifications. First of all, we wanted to check if the ground after the grouting, after this pressure grouting, was actually in good conditions to give the confinement to the tunnel. So we did a pressure meter test, a Menard test from the tunnels, from the grouting sockets. We did this pressure meter test, checking what is the E value of the ground. Also on top of that, we did a GPR to check if there's any anomaly or cavity was in the periphery of the tunnel. And third, we did a seismic topography also, just to verify what is the speed of the S-wave velocities, and to make sure that to spot any soft area, any soft pocket of the ground that still can pose any issue in my stability of the tunnel. And so finally, it's a monitoring before and after operation. We start monitoring the tunnel. We put two types of monitoring. First, optical targets in the affected rings to detect any movement. And secondly, strain gauges in the steel plates to see the steel plates were getting loaded with some load because of this ground load. This monitoring after operation, the tunnel was put on the operation, was commissioned and put in operation, was recommended to continue this monitoring during 1 year more after the operation happened. And not major moments was detected after that, and we consider the solution was satisfactory. Conclusions and takeaways that tail integrity is critical when tunneling through pressurized aquifers. So we need to watch the tail skin of my TBN, especially in case of EPB TBNs that can be an issue in case of pressurized aquifers. And we can see with this issue we had here. Ground loss can rapidly evolve in severe tunnel distortion. So whenever we disturb the ground and whenever we start having these heavy seepages, automatically this is translated to my segmental lining, which behaves not as a structure anymore, behaves like a mechanism, and start having these distortions and this cracking. Third takeaway is that the composite steel concrete lining is an effective solution to restore the lining capacity. Fully bonded plates enhance the bending capacity of my tunnel. And this solution is not only for this accident, can happen in many other circumstances. Any unforeseen situation, we design the segmental lining before starting excavating the tunnel. So once we excavate the tunnel, there can be many surprises in the ground. So this solution can be also applicable if there is any unforeseen situation, weaker ground than expected, or any other thing that make my segmental lining, once it's already designed and once it's casted in the casting jar and we have the segments ready to be installed, we prove that they are not enough. So this is just a couple of pictures to see how the solution was implemented. The steel plate was put into stages, first the bottom part and then the top one. And then the gap was fully grouted with this high-strength grout. And finally, this is how it looks like the tunnel after rehabilitation. And once was, this is before operation, but that's the final aspect of the tunnel. So that's all from my end. Thank you.